Simon has kindly offered to talk to us today about, or be asked questions today about, simulation as it relates to operations research. So I'm not even going to define what operations research is, because I don't want to steal any of the fun there. But Simon's coming. He's a professor of computer science at Brunel University, which is one of the universities in UK, just outside of London. Right? I mean, is that a good description? I mean, depends on
it's just north of Heathrow.
Yeah. So it's so thank you very much for coming today. I just really want to just start with the question is like operations research or operational research. What is it? What could you provide some context for the audience, given that this audience isn't probably where close to that domain?
Okay, yeah. And I've got to say, full disclosure, I'm a funny fish in this field because I'm a computer scientist. So most people who work in operational research are mathematicians, business school people. So the reason I'm saying that is I've got a particular view of operational research because I sort of see life as algorithms and problem solving, and people in business schools would probably say, "Oh yeah, that's the same as us." But me, it's kind of start with the maths and wind up with programs. I'm saying that because that will probably sort of give give a bit of more of understanding of how I view operational research. So, what is it? Full disclosure, just for once, there is actually a really useful Wikipedia page on operations research, which I have got up in front of me. Because if I was going to talk off the cuff, there'll be a lot of erring. The first thing to get out of the way is operations versus operational. And I've always said it's tomato, tomato. There's probably some reason why in the States it's S and in the UK and arguably Europe it's AL. But it doesn't really bother me. It's less annoying than having two L's or one L in modeling. The Winter Simulation Conference, you see, there's the first plug that I'm running this year. I was tempted to enforce double L in modelling this year, but I thought, no, I better not do that, otherwise I'll get told off. Because, of course, that's the correct way of spelling it. Anyway, operational or operations research. The first kind of example of it, there's sort of Blaise Pascal and Christian Huygens were messing around with sort of related areas in the 17th century, but and I sort of dug into this a little bit, but it looks like the first sort of person who tried whatever this mysterious field is Charles Babbage. And that's an interesting one because, of course, Charles Babbage did the difference engine and all that kind of thing. It did the first calculating engine. It's not the first computer, but it's certainly the most sophisticated calculator of its time. And interestingly, arguably, it probably launched the Industrial Revolution. The reason is Babbage wanted this very complex machine and nobody had any of the parts, so they had to go and manufacture the tools to make the parts. And I've heard an argument that then got the UK into tool making mode, which then motivated the Industrial Revolution. A side effect of operational research, arguably. What is it? It's applying the scientific method to everyday life. That's the way I look at it. So these days you hear this lovely phrase, evidence-based decision making. It worries me that there are people practicing non-evidence-based decision making, which is the inference from that. It's kind of, well, it's very rare for me to make any decisions without having, I won't call it evidence, but having an idea of what I'm doing. So for example, just a very simple example for people who are not too up with what this field is. If I wanted to travel from the north of England to London, I've got, say, three routes. I can drive, I can take the train, or I can take the bus. On the face of it, driving, it's cost per mile. Train, it's the cost per ticket, which varies by demand and time. And bus, arguably the same. And then I can start building a model of what I think about each of those. So the car, personal convenience, but motorways prone to massive traffic jams these days in the UK. Train, more expensive, fast, tendency to break down every now and then. Bus is kind of halfway between the two. It's cheaper, but prone to traffic jams as well. So I could start building a model of that, say over a few months, and then I could use that to help inform my decision as to which form of transport I'm going to take to get from the north of England to the south of England. Very, very silly, example. In other words, I'm using some kind of algorithm or mathematical model to try and help me decide which is best. My gut feeling would be to drive, but then every time I'm sat in a traffic jam on the main motorway link between the north and the south, I think I should have gone by train because the evidence indicates that it's faster, more expensive, but greener. You get the idea. So I can use a technique that helps me bring in lots of different influencing factors, helps me express them in some sort of mathematical way, and then use data to put into the formula to help me figure out what's the best. I mean, we used a similar way of figuring out if we had the Winter Simulation Conference in Seattle, how many people we would expect to be there. So we looked at attendees at different conferences on the West Coast. We looked at different factors that would affect attendance, and we sort of brought those together, not so much in a formula, but certainly in a spreadsheet, and it helped us produce evidence to present to the Winter Simulation Conference board to say that's why we think we'll get a decent number of attendees in Seattle, rather than me saying it'll be fine. So I wanted evidence to support that. So if we said back in, I mean, it says 1840, but let's say the sort of early to mid 1800s, that emerging mathematicians were starting to use techniques to investigate real world problems. It's kind of, there was a bit of a gap. And of course, if there's a bit of a gap, it means that it probably continued, but nobody was talking about it because it became a kind of normal thing to do, I would argue. And then, unfortunately, we get to the 20th century and wars started happening. So the First World War used some operational research techniques to gather evidence to help plan better in the war. And the two main things that happened there was convoy theory, so the development of mathematical techniques to help us understand what's the best way of moving shipping and cargo around in a wartime environment, and Lanchester's laws, which there's a lot of people that don't know about these. These are using operational research techniques, mathematical techniques at the time. A set of algorithms were developed to understand if you've got a certain mix of forces attacking another mix of forces. Lanchester's laws, which were derived from evidence-based observations of the real world, gave us simple rules to understand after a battle who would be the winner at a level. So it's a very high level thing. And Lanchester laws are still used today.
Thank you.
Then we move on to.
I just wanted to interrupt, Simon. I just wanted to know that Chick Macal has joined us as well. You may not.
Oh, great.
So he's as well. So just Chick, just to let you know, Simon's just given us a introduction to what operations research is. I'm an operations researcher myself, and it's always that embarrassing fact that we're the one subject that needs to explain to everybody what we are, whereas everybody else tends to already, doesn't have to go through this. Sorry, Simon, to interrupt, but I just thought I'd let you know.
No, it's fine. Hey, Chick.
Hello.
Glad you could make it. So kind of, yeah. So you got convoy theory and Lanchester's laws in World War One, and then we head into World War Two again. You got that sort of effect of war advancing science, which is an unfortunate duality that you get very often. But lots more operational research techniques developed during World War II. I don't really want to go into what the applications were because they're not particularly savoury, but you can guess. And then after the wars, we moved on to the 50s and 60s, and then we got sort of the emergence of what you probably call management science. So the application of these techniques to business. So you've got industrial engineering coming out in the late 50s and systems dynamics with Forrester. You've got, I mean, Chick and I, we work a lot in simulation. So when the real world starts getting a bit too complex for mathematics, we start heading into algorithms and simulations. So in the early 1960s, you got Tocker working for, I think it was UK Steel or General Steel, but he started applying operations research techniques to the production of steel. And arguably that gave rise to the first recognizable use of computer simulation to do this. And on we went. How's that as a start?
That is very good. Thank you very much. You've actually covered several of my questions.
Well, I'll be back next week for more.
Thank you. But I think that was a really nice introduction, and I think maybe at this point it's also just worth pointing out. So Simon is the general chair for the Winter Sim Conference, which is the oldest simulation or continuous simulation conference that's been going on since was it the 50s or the 60s?
Andrew, it's not continuous, it's discrete.
Oh, okay. All right. You have to give that. And also Professor Macal, Chick Macal, who's from Argonne National Lab, and it's the University of Chicago, was also the general chair a few years back, if I remember correctly. Between them, so they're very involved in the simulation world as well. So I know we're talking about mathematical modeling here, but that leads into my next question, which is would be for both of you now. So we got an idea what operations research is, but how does your background fit especially in relation to the agent-based modeling simulation within that domain? So how giving a little bit of background. Then Chick, do you want to go next, and then we go back to Simon so we can swap back and forward if that's okay?
Sure. In terms of my background, I actually have a PhD in operations research, and from Northwestern. And when I was at Purdue earlier, I had a master's degree in system simulation with one of the founders of the field of simulation, A.L. and B. Pritzker. So I've seen simulation grow up within the operations research community, which is from where it came. And the real emphasis was on modeling stochastic processes with the computer for systems that you couldn't solve analytically, like queuing theory models. And that led to the field of discrete event simulation, where, it's applied to things like modeling, waiting lines for bank tellers and checkout counters and things like that, and very complex queuing situations. So that really is how I got into simulation myself. And it, then advanced, discrete event simulation advanced through creating simulation languages like GASP and in the early days. And, there's others now that, we're familiar with. But eventually, discrete event simulation kind of morphed into object-oriented simulation. And then more recently, like starting in the 90s, because computers, advanced. We didn't have, look, in our early careers, we didn't have computers. I don't know, maybe Simon did, but we didn't have computers. So eventually when computers got to the desktop level, then simulation became widely used. And that led to agent-based simulation, which came out of really not operations research, but more the social sciences and dabbling into the social sciences. So it was easy for me with my simulation background to pick up agent-based modeling and simulation, which I've been doing continuously not discretely, continuously since 1999. All I've done is agent-based modeling and simulation. In fact, here today, I'm at the SPB BRIMS conference at Carnegie Mellon, which I saw you a couple of years ago at, Andy, yourself. And I just came, the reason I was late, I was giving a tutorial on agent-based modeling and simulation.
Thank you. I appreciate that. Thank you. Simon, do you want to give a brief introduction to just your background, how it relates to agent-based modeling and simulation? Oh, you're muted. You're still muted, Simon.
I can now think again about what I was going to say. It's I started life as a complete geek, so I think I got my paws on a computer when I was 12 or something like that. But the school I was at, we still had slide rules, so that'll give you an idea of how young I look for my age. But it's yeah, I was the last year we used slide rules. We didn't make a transition to computers whilst I was there at all, but um, we had the sort of clunky old Apple IIs and then a whole load of home computers. So I had a big interest in computing. But I also realised that might not be a good career forward. So I ended up doing an industrial related degree first. And in the final year, we had a module on discrete event simulation using Hocus, that's a good one. If anybody can Google Hocus, it'll show you one of the original simulation languages. That got me really interested. I was also in Sheffield, which is arguably one of the birthplaces of discrete simulation. I mean, Chick mentioned Alan Pritzker. That was another, major driving force in the US. But I soon discovered there was quite an undercurrent because British Steel had a lot of effect to the universities in where I was studying. Anyway, I went on to do a computer science degree, and then I discovered parallel computing. So I had an interest in simulation. I had an absolute fascination with parallel computing. So I then went on to do a PhD in a field that is kind of at the edge of mainstream simulation completely, but I did a PhD in parallel simulation. So the hardware I was using has vanished now. These chips were called transputers. They were building blocks for highly parallel systems. They were fascinating things to use. I wanted to try and speed up simulations, but the observation I had of research at the time was there was a huge gap between what people were doing in parallel simulation and what people were doing in business and industry in terms of simulation. So I tried to bridge the two together by creating. Now, here's something that people have probably forgotten about in computer simulation: worldviews. So we talk about discrete event simulation, we talk about agent-based simulation, but in discrete event simulation, we actually have different flavors. And the principal ones, when people look at textbooks, are event-oriented, activity-oriented, process-oriented, and three-phase approach, etc. But those are the main ones. So I tried to create flavors of parallel simulation that sort of leverage that. So something that would be recognized. So a form of parallel simulation that would be recognizable for somebody who is a mainstream discrete event simulation person. But it kind of didn't work because it was still far too complex, really, to do. But I learned a lot, and it kind of influenced a lot of the things I do even now. Which is, I love technology, but I realize there's lots of people who don't. So try and understand the problems you're trying to solve, the things you're trying to make better, and then absolutely apply the technology in the end user's context. So in this case, it's operational researchers who use simulation. How can I make their lives better through technology? So that's kind of the relatively brief background.
Oh, thank you. That leads me very nicely into the next question. So part of the reason we're having this series is we realize there's a lot of different communities using agent-based modeling simulation, right? And we're trying to understand those communities. Now, one thing that's come up, I've known in the past, is that, within the OR community, that simulation has been derogatorily labeled the method of last resort. Could either of you want to talk about that? I mean, where that is right now, and what's your view on it?
Well, I'd love to chip in and talk about it and hear what Simon has to say then too. You're right. When I was studying simulation, and this was in the mid 70s, right? there was an operations research book that was published by a famous operations researcher. And the last chapter of the book was about simulation. And the quote was, when all else fails, simulate.
Yeah.
And so, in a sense, simulationists have always had the chip on our shoulder since then, you know. And the whole idea of, I guess, the science part of operations research is to like derive some universal facts or theories or equations. You know, Little's equation is, it's been said, and is one of the, which is queuing theory related, is like one of the only true, operations research theories, contributions to science. That's a general law. It's been said. But in any case, I think that we've come a long way for people regarding computation as actually forwarding science and not just being, a computational simulation model, not just being some arbitrary thing that is kind of like hobbyists do, but it doesn't really enable you to learn anything about the systems, you're supposedly modeling. So, but there is another saying that came out in the earlier days, decades ago, that was like, we're modeling for insights, not for numbers. And I think that holds true amongst knowing really what that is amongst simulation modelers. We're just using the models to derive observations and ideas, and then going on to explain that to decision makers, for example, in words without referencing the model. You never say the model said this or the model said that, because with the model, you've come to some new idea or conclusion, but you've also got the reasons behind that you can back it up with. So I think that's been really an important development. But more recently, people are understanding that not all systems can be analyzed and derived equations from. They simply have to be computed. They are simply not reducible, to anything shorter than a computer program, really. So,
thank you.
Yeah.
Simon, did you have anything you wanted to add?
Yeah, it's Chick, when you were saying about the sayings, I always remember Ray Paul, who was an absolutely brilliant professor of simulation. He came up with possibly the worst acronym in simulation, but the most memorable, I'd say, is SINSFIT, which is simulation is no substitute for intelligent thinking, which is absolutely spot on. That you get
Right.
sort of people who believe in the model and almost like sort of priests to a shrine. They keep the model going, they worship the model, and what the model said is right, but of course it isn't. It helps to give us evidence to make good decisions. And
Yes.
that phrase that simulation, the method of last resort, and all that kind of thing. I still understand why people say that, because it's. I'm going to get shot for saying this, but it's a lot more complicated than using maths. Because when you go out of mathematical formula, you've got to start learning. I always encourage people to learn how to program, but there are lots of software tools you can use to do simulation. And then there's a whole load of things in there. You've got to understand how to communicate with end users, because if you don't have the stakeholders along with you, if you're trying to solve business problems, and the model's worthless because they won't believe in what you're talking about. There's a lot of lessons there for AI these days, because you bring the user with you ideally on the whole journey. There's language issues. We talk about confidence intervals. We never talk about confidence intervals to the end user, because that comes over as being extremely wishy-washy, and we know what that means. It's not wishy-washy. So I tend to talk about risk instead of confidence intervals. And in business context, that makes more sense. But it's kind of there's a very broad range of issues. Now, Andrew, I told you I've got a cold, so you'll have to tell me the question again. Where are we going with this?
Well, so the question was, it was just more the I just wanted to get that flavor, that the idea behind it. And I think you've answered it very well, both of you, which is, you know, as in with all domains, there is issues within that domain, and operations research has had a particular long issue with some people seeing it derogatory. One of the things I was going to ask you later on was about this. There is that subgroup within this operations research community that says the only thing that's operations research is optimization. Everything else is operations research. And I might as well ask that now. I mean, obviously, I'm guessing the fact that both of you are working in simulation, you disagree with that statement, right? But do you have any comments or maybe on that at all, or any?
Well, I'll say this immediately. I mean, so Chick and I talk regularly at the moment because Chick is my link to the winter simulation board at the moment, and that's a nice excuse to sort of chat and catch up with life, the universe, and everything. I sort of raise sort of the view I have of the world, which that we're very tribal.
Yeah.
So in operational research, that's extremely the case. I mean, the air communities in operational research, we've got to say, there's a lot of academics in this, that they sort of have close shop views about the world, but then when you start challenging what their assumptions are, it kind of falls over pretty quickly because, it's, at the end of the day, we're trying to make the world better. And there's only a certain number of assumptions you can make to make the mathematics more convenient before what you're doing is not particularly useful. You get this in the machine learning community. There's a lot of research in machine learning that's for the perpetuation of machine learning. You wonder, is that directly translatable into anything that the world can use? So I think this business about, community X says this is the only worthwhile one is really as symptomatic of that actual community. I don't like that. I've got to say the computer simulation community that Chick and I work in, there is a little bit of that, but it tends to be a lot more open-minded about things up to a point. We start talking about verification and validation of agent-based simulations, then that wanders back into the room again sometimes. But I tend to find, because of this, is a confluence between management scientists, computer scientists, domain specialists. There's a bit more open-mindedness about things.
So your argument is that because by the nature of what we do in operations research simulation, it's bringing people from different domains together, that almost creates an open-mindedness that maybe wouldn't be there if people are just specializing in a certain domain.
Yeah, I mean, it's I mean, the UK has got the Operational Research Society, which is a brilliant organisation. Globally, we've got Informs. So I can't remember, it's OR and management science. You wouldn't have fantastic societies like that if we just had people who did optimization. And you look at the special interest groups in those, and you look at the conferences and you look at the tracks, and it's such a rich, exciting field to be involved in. And one of the things I love is you've got the theoretical end, you've got really interesting theoreticians there. And then you got the practical people who need problem solved, which, sometimes you think, oh, why have you done that? That seems a bit weird. But then you try and understand where they've come from. And to be honest, every time you do that, you talk to a new person in this field, you sort of, there's another bit of the jigsaw, another bit of learning. It's you're never bored in this field. But the point is, it's a very broad church. And you wouldn't get that if you were just sort of looking into one aspect of it. I mean, saying it's optimization is almost like saying, well, the world is linear programming, which is just silly.
Right.
There are many, many other fascinating facets to this subject area, as demonstrated by the breadth of the Operational Research Society and Informs.
Thank you. Did you have anything else you wanted to add to that?
I think that well, like when it comes to Informs, right? It's pretty much standard operations research, management science. at the Informs conference. There is a special interest group in simulation as part of Informs. So, um, but I think that for the most part, the publications of simulation, simulation related, are less frequently appearing in the operations research, journals and things. And basically, the simulationists said, well, we talk to each other, we have common interests, we'll just make our own journals, we'll make our own simulation societies, and we'll appreciate what each other does because we do it too, unlike most of the other aspects of the operations research community. I mean, I've been a member of Informs, since I was in college, and up. So I see what the perspectives are, but I think that this inclusivity, I think that we have in the simulation field has to do a lot with the fact that if we're going to really build a simulation model that has an impact in the real world, we're going to use real world data and we're going to talk to real world experts that maybe don't know anything about simulation, but know about the systems that we're modeling. And so, that's kind of, I think, a side effect of the simulation community itself. We're very interdisciplinary and inclusive. And I do remember a conversation I had with Alan Pritzker when I was in school. We were talking about my research work, and he says, well, what exactly is research in simulation? He put that question to me. And, it's a good question because in operations research, really, a good operations research paper derives some theorems, some new theorem, really, by the way, with my work at Northwestern, since this is before the years that Barry Nelson came to do simulation, when I went to Northwestern, there was no simulation program whatsoever, no course even. So for my dissertation, I did work in optimization theory and, highly nonlinear complementary programs and things, So I've kind of seen that whole thing from both sides,
Yeah.
So it's a good question. What is simulation research? And this is something that Simon and I, of course, struggle with being the, editors or having, Simon having been the editor of the journal Simulation. What is this? Somebody sends an article in on a simulation model. The question is this research? Is this adding to knowledge that what people want to know about? Things like that, And so we have to use a fine kind of knife to parse out what actually a research contribution is in the field of simulation, and then put it in the journal. So, yeah.
Thank you. Thank you both. So our audience has been waiting patiently because I said I would have the complete dominance of the questions for the first part of this talk. But now I think I'd love to open it up. I do have more questions and I can always go into those if I want, but do we have any questions from our audience for our two guests today, Simon and Jick? Don't be shy. Oh, we do have. Okay, Michael, do you want to just jump straight in?
Sure. Hello. Thank you for your words. It's been stimulating. I'm somewhat in an adjacent space. One of the things that's been running through my mind as I've been listening to you has been, oops, sorry. There I am.
I get that a lot, Michael. It'd be helpful if you could just introduce yourself because you know us, we don't know you.
Yes. Well, that's a good question. What are my labels? I do have, so this stream is in Washington, D.C. It's on Piscataway land, unceded. And instead of using Washington, D.C. in recent times, I've used vocabulary of natural systems, living systems, and indigenous people. And so I've become ever weirder in the ways in which I label the world and then come up with theories of causation about them. And this kind of gets at the question that I wish to offer. Because my original training was as an economist, and so what was quantifiable and the ways of measuring that were available were the ways in which one could make the best or most confident predictions, right? This is not new. But sometimes our theories of change. And to give you an example, in economics, everything was denominated in dollars, but its impact, growing the economy 3 times over in 60 years was possible. Growing happiness has turned out to be a blind spot from economic activity up until about 10 years ago, when people started looking at things that were not so directly quantifiable or currently tracked. And so the idea of what is the evidence we have? What is the evidence we don't have? And how do we talk about this? And so this comes to the question in the world of development evaluation, particularly in other words, after the projects have been unfolding, there's been what are some principles that have been learned about what to do to manage the things that you don't know when you start. So your simulation models, your project planning assumption, all of these things are part of our methods. And what are the kind of things that can be done to better anticipate what you didn't know at the onset? And there have been 3 principles from about 100 years of digestion of the research, and these 3, which have come up in this conversation, have included looking at relational dynamics across the space, multi-perspectivity on the space itself. So there might be, how does this discipline look at the 6 blind men looking at the elephant syndrome? And the one that is the question that I wanted to throw out was this idea of boundary definition. What is the boundary that we're all looking at, and how do we track as we discover new things? What is the boundary that we're continuing to simulate, to model, and so forth? And so this question of what is inside and what is outside, and how do we talk about as we co-think differently about the space that we learn about turns out to be a gigantic problem in the learning space. And so I know that was a long question. I'm not sure. It was, please talk about boundaries. How do you talk about boundaries over time? And I hope that long-winded intro was sufficient to spark something. And if not,
Okay, well, I'll just jump in with sort of something very quick and simple. There's you come across soft systems methodologies in operational research. There's all sorts of different, the names have evolved over time, presumably as people want to get more research from, they call things differently. But it's this kind of idea, which at the time was revolutionary, that you work with the people in your community to form a rich picture of the system that you're trying to model. And Peter Shecklin, I believe, and this might be apocryphal, who did start doing this. I think he used the phrase rich picture and then was moderately astonished to see people are actually drawing pictures. Pictures for me are great, the non-technical interpretations of systems. And of course, in that, you're going to have a boundary. So what's the right boundary? What's the wrong boundary? Well, it depends on the problem that you're doing, and it depends on the people who are taking this journey with you. And then do these change? Well, now this is where I've got to say, are you delivering a contract or are you doing research? 2 very different things. If you're doing a contract, then boundaries won't change, ideally, because then you have to charge the end user more money. But in research, that's fine, because then you're reporting how the interpretation of the system is changing over time as you take these people on the journey with you. You might think, well, okay, the boundary's got to get bigger because we didn't understand that we needed to involve that factor in there. How did you know that? Well, it was a result of the people who, through you being an operational researcher, you being a modeler, you're educating them into how to systematically view the world. And as they're doing it, arguably they're thinking in more detail about their system and realizing, actually, we need a little bit more depth over here. Depth is a change in boundary. I'm okay with that. Does that make sense? Over to Chick.
Well, I look at, when I hear the term boundary, I kind of, with respect to modeling, I usually look at systems. There you got the real world, and then you're modeling a system, which is basically a subsystem in the world, and you kind of draw, a circle around it, so to speak, and that's the boundary of your system. And then within that boundary, when you're going to make modeling decisions, you've got, and so the boundary is the breadth. And then within the system, you've got the depth. And typically, at least in the world of agent-based modeling, we talk about, granularity within for the depth. And the granularity is three things. It's time and space, right? The physicists tell us we have those two things. And then, agent modeling tells us we have agents, as in, they could be people, depending on how granular we want to go to. We could go down to the sub-person level and model a person's organs, or we could go and model the cells within organs, et cetera. So there's this notion of multi-level within the boundaries. But, in practical terms, like when we were modeling COVID, for example, we were modeling everybody in Chicago because that was who we were, decision makers. We were reporting on COVID spread to the Chicago Department of Public Health and the mayor of Chicago, because they wanted to figure out what actions they should take depending on how much spread there could be, in the coming 2 weeks in the community, right? So, but the boundary was the people in Chicago. So we modeled all their interactions of people in Chicago, people coming into Chicago, interacting with people, but we had to just arbitrarily define outside of Chicago as the boundary, And so we always had questions about what the boundary effects are. Maybe if we included the surrounding counties and all the people in there, we'd get a different result. So we just had to make the boundaries and as an assumption without regard to what we knew of the sensitivity of defining the boundary to the ultimate results and the recommendations we were giving. So, that's kind of how I think of boundaries. I mean, in other words, I don't know what, we don't have any good ready methods or way to think about boundaries that I'm aware of.
Yeah, well, it's a fascinating thing. There's a colleague, a friend of ours, Stuart Robinson, who's the dean of the business school in Newcastle University in the UK. Stuart has written a lot about conceptual modelling, and I believe I'm probably massively misquoting him. He uses phrases like "just enough," the conceptual, just enough detail. And how do you know that? Well, he's a very experienced modeler, and it's coming back to, well, he's the conceptual modeler, the boundaries of the conceptual model, right? Well, it then becomes the art on experiencing the person doing the modeling and how they interact with the people in the system. Now, I don't know how many people know Stuart, but he's an absolutely excellent communicator, and he's just, he's the right guy to bring into complex situations to actually get to the bottom of what needs to be modelled, because he is an excellent communicator. He's rather charming. So that's an important tool. And sometimes I think in wider operational research, that's often forgotten, that it's often the qualities of the person doing the modelling is a very important factor in what's being modelled. So, if somebody's doing the modelling and they're lousy communicator with human beings, well, that's not a great start. You're not going to get the stakeholders, the systems, to open up about their system. Similarly, if they don't have the technical expertise to actually then start building models, which might not necessarily be a simulation model, it could be any kind of model. then they're going to come up with something a little bit naive. So the people who can effectively set boundaries, which are in turn set by the stakeholders, and then model the system within the boundaries, it's a rather special kind of person in there. And I'd argue they're even more special when they do simulation, because you have to have so much more knowledge about programming and systems than you would do, if you're using simple mathematics. But yeah, at the end of the day, it's, boundaries, right or wrong, it's the people involved in the system, and it's the art of the person doing the model that sets the boundaries. And if they are correct, then it's because the person who's doing the modeling has done a very good job. Now, very interesting question is, two modelers come along and model the same system with the same people. It's a special situation because I've just created two universes, so we're starting from scratch both times. I can guarantee the two people doing the modeling will create two different models, and that's a whole interesting set of discussions. Unless we're modeling a simple job shop, then it would probably be the same. But of course, life is a lot more complicated than a simple job shop.
Actually, thank you, Simon. So, Stephen, I'll get you in a second, but there was a question in the chat, and I think this leads directly into that point. The question was, how do you deal with the intangibles, the soft variables, right? I mean, what's your strategies for dealing with these?
I think that's really, sorry, Chick, to jump in, but that's a nice one. But can we get an example?
Well, emotion, it could be something that we might, if we got human agents in the system, you may want to model emotions.
Well, that's now, yeah, there's a lot of research in that, and I'll defer to Chick.
Okay. Well, I'm kind of, I'm an engineer at heart, so I'm always looking for the practical approach to take, how to model this, how to model that. The emotion thing is, the way I look at it is this. Looking again at agent-based modeling, an agent takes in, senses things from other agents and from its environment, right? That goes into the agent. And so there's two possibilities that come out of the agent, or maybe both come out. But one is an agent takes an action. Okay. We know what that means. Agent has a behavior, takes an action. Could be move somewhere, or maybe it, goes to the hospital or something because it's sick. But then the other thing is that an agent we may be modeling its emotional state, or its thinking state. Maybe it doesn't take an observable action, but something happens that changes how the agent feels about something. And so I was just using this example. If we're modeling social media, which I've done, social media networks, we want to model how agents feel about different topics, right? We want to model their basic, if they are asked to express an opinion, we'd want to find out what their opinion is. We'd want to model that. And so one way that it's been done is to simply model model how agents' stance is with respect to various issues through what's called valences, which are basically numbers between -1 and 1, where 1 is like and, -1 is dislike, 0 is neutral, right? And, you can create an opinion model based on what the agent's valences are on a number of subjects. So you might have a model that says, who are people going to vote for in the next election? Because you kind of understand, though, where people stand on different issues. And that's an effect. It sets up for kind of an emotional response at some level. One other thing I will say, though, that I've been reading a very interesting book lately. It's called A Brief History of Intelligence. And the author in that book really goes through the nervous systems that developed in animals and vertebrates and leading up to humans. And, you can see where it's going. It's resulting in, LLMs and things, in the end. But he does talk about how affect or emotions could have arisen in intelligence development or nervous system development. It's kind of like emotions arose basically as a way to help people or organisms decide things to do, you know. So anyway, I'm just throwing that out there to support Simon's idea. That's a lot of interesting things going on in how to model soft things like emotion that we would readily incorporate into agent-based models.
Okay, so it's the things are evolving, right?
Yeah, well, yeah. Just to add in, I mean, something came up in the chat just then, but it's interdisciplinary. I mean, we're not the first community to say, how do you analyze emotion? So, I mean, I was involved in a project a while ago about sentiment analysis of tweets.
Mm-hmm. Right.
How do you sort of pick up sort of the direction of travel of how people are feeling as they tweet on a particular subject. And that came down to individual words, and the words had scores associated with them. And basically, you analysed a bunch of tweets, added up the numbers, and that would give you a rough comparative value against another set of tweets. Now, is that right or is that wrong? I don't know, but it's a technique that a community has used to do something. Marketing has got a lot of research on how people feel about things like that. But
Mm-hmm.
at the end of the day, you've got to kind of start off with, like, the assessive emotions or whatever, and then eventually get to a set of numbers you can put in a model. So, like you say, Chick, I mean, the valences, I think, is a really interesting idea. And then you've got to sort of look at what the model's actually doing. Is it helping you to test theories about emotions in a particular situation?
Mm-hmm.
Or is it helping to get insight about the emotions that exist and what happens to that system? So, but the fun thing in simulation is there's tons and tons of research that's not been not been either done or not been done to death. And the representation of emotion in models. I know in complex adaptive systems, there's a lot of mathematical representations of emotions. Now you bring that out into an operational simulation is a fascinating area as well. Lots of things to do still. Lots of things to do.
Okay, thank you both. So I'm looking at the time. I think we're going to take Stephen's question, and that will be our last question, and then we'll wrap it all up. So thank you, Stephen. Over to you.
Yeah, thank you, Andy. And hello. It's been maybe 15 years.
Yeah. Hi, Steve. Good to see you.
Yeah, so I attended Winnipeg in 2004 and 70 simultaneous spots. I was kind of an outsider, never felt more alone.
Having a little bit of trouble hearing you, Stephen.
Oh,
You're very, very quiet. Is there any way you can speak closer to the mic?
Yes. How is this? Is this better?
Oh,
much better.
Yeah.
Okay, good. Yeah, so 2004, I attended the Inform 7 simultaneous tracks, as you know, and never felt more alone at a big conference until I ran into Chick, my old friend from Arrowhead Conference and San Francisco. So, and then you were a great mentor, Chick. My question kind of is on the research side. So I kind of lump, and this is computational social science group here. And in scientific computing, what does computing mean, right? And different disciplines, all disciplines have a computational these days, biology, economics, physics. And I'm going to focus on the questions around the fourth one, Chick. You can argue about the first three, but I think of the first one is kind of your career numerical solutions in the early days, and then later simulation. And in the last 20 years, machine learning, AI, computational statistics. You can argue about what the categories are, But the fourth one is looking at the system as actually doing computation, right? And this kind of goes back to Crutchfield and others, Edge of Chaos, a little bit of Wolfram, that when a system's at a phase transition, it supports computation. And then the other thing that I think is universal, whether we're looking at living systems or economic systems or operations research or operational research with discrete event scheduling, what is action in these systems instead of minimizing energy or maximizing something? But in operations research, you might be setting a high dimensional weighted fitness function like minimize cost times time. In physics, we have momentum times position or energy times time as action.
Yeah.
And so my question is, as research, what does it mean to look at a system and understanding that it's computing least action paths before we even intervene in them? And understanding, if we watch the log files, what part is the platform or the chip, so to speak, and what part is the code? And how do we as computer scientists look at systems like that to understand how we can intervene in the sense of compiling a script to that platform?
Wow. That's a pretty good once over the big questions of everything. Well, it's it's hard to know where to start, but I think we're and this relates back to the operations research part and what operations research people try to do. I think we're just now maybe coming to the understanding that these things are irreducible. These systems are irreducible. They can only be computed. There is no reduction we're going to find or magic simplification. It's just, it is what it is. And this goes back to, Wolfram and in particular, new kind of science, with his rule 30 or whatever it is, these the simplest rules possible produce completely random behavior, at some sets on the edge, as you said, on the edge of chaos, right? It's all about on the edge. And so this goes back to Chris Langston's, artificial life stuff, right? Life only exists on the absolute edge of chaos between stability and complete instability. Um, so
And just to mention on the game of life, say you've seen the last 15 years where people are now compiling programs to run on the emergent dynamics of game of life, as an example. And that's what I mean, like.
Okay.
That's kind of the theme of my question. Yeah.
Oh, the emergent, you mean to recognize it, so the entities recognize their emergence, that they're part of entities or something?
And how do we see that systems are potentially computational systems that are perceiving and acting, whether it's a supply chain or a city or a body?
Yeah. Well, that's I don't know. I mean, that's really the state of the art stuff that we're at. It's kind of like the system, things emerge in the system. What's really going on? Are there conservation laws like you suggested, or Crutchfield went back to, I remember the early days at SFI and those early papers and things. I mean, it's just, these are some of the mysteries that remain for science. And, just back to Wolfram, last thing I'll say, because I don't really have anything else to say, but, Wolfram, has his research program now at the New Kind of Science, where the whole idea that everything has to be computational and it can't be reduced below that. Okay. And so then it's the search for the rules, basically in the universe that kind of, and, they could be simple, very simple rules that are governing how the universe is actually unfolding and progressing in all things, including social system and social dynamics. So, it's kind of a concept and a hope for thing that we need to look for the rules in nature and find out what they do. It's also related to stuff that, Josh Epstein is doing, right, in social sciences, like the inverse problem. Here's
That's
the
right.
data. Now tell us the model that produced it,
And the platform. Yeah.
Yeah. So I'm with you. It's interesting. I should come down to Santa Fe and talk to you more next time.
And I'm in Boston, and I'll be out at Northwestern with Uri. And by the way, the UDown Prize, congratulations to Uri winning that prestigious award.
Yeah. Yeah. Uri won some big award.
Oh,
I
you're
forget
still
what
in
it's
Chicago?
called. Yeah.
Yeah,
Yeah.
so
Yeah,
sorry
I'll
to
be at that
interrupt,
during
folks. So just
Okay.
because
Anyway.
we have gone over time.
Yes.
So
Yes.
I'm going to stop the recording now, and then we can carry on. But thank you both, Simon and Chick, for being here today. This clapping for the whole crowd. Really appreciate this. I think you gave a fantastic introduction to operations research and how that relates to the simulation world.